what I'm going to work through here is another SN2 type reaction. In fact, I'm going to use the same substrate as before, but I'm changing the nucleophile, and because I'm changing the nucleophile a little bit, what that's going to cause is a acid-base follow-on reaction to be necessary in order to complete the final mechanism to end up at the final products. And so largely this is going to be an SN2 reaction, and then we're going to couple on a little bit of an acid-base thought to the end of it. So once again, we have a secondary substrate, and this is specifically going to be the R stereochemistry, again, of the bromobutane. And I'm going to react it, in this case, not with a minus charge, but with a bit of methanol. And so the solvent, once again, I'm using DMSO because that's a relatively good SN2 type solvent. But in order to get this reaction to go, because I have kind of a crappy nucleophile, it may be necessary for me to heat it up. So if you see a delta, that's what it means. Maybe I need to heat this reaction in order to drive it to get it to go. None of the SN2 step is different from what you've seen before. The nucleophile is again going to be an oxygen lone pair, although it's not a particularly good nucleophile this time because the oxygen lone pair is on a neutral oxygen. But nevertheless, it can be a nucleophile, and it will go ahead and attack the sigma star bond, the sigma star orbital of the carbon-bromine bond. And so the LUMO here is once again going to be the sigma star, and the HOMO is once again going to be the oxygen sp3 of the lone pair. And this goes ahead and happens. And so the intermediate that I form first is going to be one where the bromine has already been displaced, but now instead of having a final compound, what I have instead now is some intermediate. And the reason why it's an intermediate is because the hydrogen is still bound to that oxygen. So initially this oxygen had two lone pairs, a methyl and a hydrogen, and the result of this arrow says it's going to make a bond. So in English what this arrow means is this oxygen lone pair is becoming a bond between the oxygen and that carbon. And so now I have three things bound. There's a lone pair left over that has not reacted, I have a hydrogen left over that didn't do anything, and I have a methyl left over that didn't do anything. And now I have a new bond. And so overall I need to have a plus on this oxygen because it has three things bound and only a single lone pair. Meanwhile, of course, the result of this arrow in English is the carbon-bromine bond has become a bromine lone pair. And so nearby I'm going to have a bromine floating around that now has four lone pairs on it, where originally it had three, and it now has a minus charge. Okay, so that's just floating there. Now, what happens next? Well, in principle, two different things could potentially happen. One is vastly more likely, and one is less likely. So the less likely possibility is that the bromine can come by and simply abstract this hydrogen right there, which would cause this now to push its lone pair down there, and that would then lead to the product that you might expect, which is to say we're going to end up making this methyl ether, and specifically the stereochemistry will invert as a result of the SN2 reaction. And so keep in mind that what's happening in these first two arrows is this is an SN2 type mechanism. And then this arrow that I drew here, the set of arrows that suggests that this bromine could abstract that hydrogen, is in fact kind of an acid-base reaction. And so that could be what's happening there. Acid-base after the SN2. Now, why is that relatively unlikely? Well, a bromine is the counterion of a really strong acid. So the pKa for HBr is, of course, about -9. It's one of the strongest acids we have. And so the only objection I have to this mechanism is that it's exceptionally unlikely that bromine is going to be the thing that deprotonates. Because the pKa of this protonated species as it stands right now is on the order of -2. And so what that's saying is there's a 10 to the 7th gap between these two. It's unlikely that this will be the thing that deprotonates. But if it did deprotonate, you would make that, and HBr. So rather than that being the thing that's most likely to happen, I would suggest that what's more likely is that you have some leftover methanol that has not yet reacted that's still floating around, because when you mix these together, presumably you had a lot of methanol and you had some of this and so on. So what if the leftover methanol is the thing that does the abstraction? So the exact same mechanistic thought, it's just that this does it. And again, the pKa for the alcohol going to become a protonated alcohol is -2. And so this is at least neutral in terms of pKa. All right, so the big picture idea is that first you do an SN2 reaction to form this protonated species, which is then relatively easy to pull that hydrogen off. And the most likely base for this scenario is going to be an unreacted methanol that just happens to be floating around and comes and pulls that off. Also somewhat plausible, but not as likely, is Br- coming by to pull that off. Either way, the result is the same. You end up making this ether as the primary substrate. And for bookkeeping's sake, often what you might see is that HBr is the byproduct, but that's just because you end up losing an H from there and a Br from there, not because that's the most likely scenario in the reaction. Again, acid-base would argue that you're not going to be using using the Br- to do the deprotonation. So the last thing I want to point out here is what the reaction coordinate diagram for this process would look like. So what we have so far is a set of starting materials where we have a substrate with a leaving group bound, which is to say this secondary bromide, and we have a nucleophile, which is to say this methanol. And then it goes through an SN2-like process with the typical one hump sort of transition state, but in the middle here, what you end up with is having this protonated oxygen species, which doesn't exist for very long, but clearly is going to be an intermediate. So it hangs out there for at least some lifetime before it goes on to the final products, and the final product is simply the methyl ether. But don't imagine that this is an SN1 type mechanism, because fundamentally the only reason why we have an intermediate here is because we are coupling together two different reactions. First, we have an SN2 reaction, and this is the SN2 proper, but it turns out that that intermediate is not particularly stable, and so you can't isolate it. But after an acid-base reaction, then it goes to a more stable product, and that is the thing you isolate. SN2 process gets you to the intermediate that's here, acid-base reaction then takes you on to the final products. So it is eminently possible that you will have an SN2 reaction that's coupled to acid-base, either because you do the acid-base first or because you do the acid-base second. So right now, of course, we did the SN2 reaction, which made this into a more acidic proton, which could then be pulled off, but there are certainly cases you could imagine where first what you do is take this, make it into a better nucleophile, and then allow it to react. Bear in mind that if you were to draw out the mechanism of this reaction on, say, an exam, you would not be able to invoke an O- to do the reacting because there was no base present in the initial reaction. The initial reaction just simply had methanol, this substrate, DMSO, and heat. So that doesn't allow you to use O-. However, you can draw out the mechanism the way we did, and that leads to a plausible outcome. However, if instead of giving you the OH substrate here, we had given you an O-, then of course you could imagine this reaction taking place in standard SN2-like process, and the acid-base would not be illustrated. One more point to make here is, of course, even though there is an intermediate here, that doesn't make it an SN1 reaction. What differentiates an SN1 reaction from an SN2 is the presence of a carbocation in the actual process between reactant and the substitution. So an SN2 reaction is one single step between reactant and the substituted product. This acid-base reaction is separate, it's just kind of cleanup. So this is an SN2 reaction with an acid-base chaser.